Hi, I hope everyone is doing well. We're going to start on lesson 3 in week 2. I hope everyone is uh, happy, healthy, and safe at home. Um, Last week, many of you did complete the assignments on time. Thank you so much for doing that. And those of you that I did talk to with questions, feel free to reach out to me again. Those of you that did not reach out and had questions, don't hesitate to reach out with anything that's going on this week. This week, we're going to take lesson 3, and I'm going to divide it across a few videos. Lesson 3 is on universal gravitation. It is the capstone topic of our Physics 1 mechanics chapters. It is going to focus on what gravity is and how it interconnects with many of the other topics that we have talked about previously this year. To make sure that you can quickly access some of the content that we're covering and go back to it quickly, I'm going to divide up the lessons. The first lesson is going to talk specifically about forces and the acceleration due to gravity, and then we'll move into lessons on the other interconnected topics relating to gravity. So here we go. So again, in lesson 3, we're going to talk about Newton's law of universal gravitation. Newton's law of universal gravitation was one of the topics that Newton discovered, came up with when he was, like you, home on quarantine. The plague had traveled through England, and I've talked about this for years in my class. I say, could you just imagine? I would say this for years. Could you just imagine you were sent home for school for 18 months? And that's exactly what happened to him. He was sent home. They said, come back when the plague has passed. Now we personally can experience some of what Newton had experienced. And while he was home, he was doing some research. Hopefully some of you are out there. Hopefully all of you are out there exploring some of your topics of interest in our time at home and catching up on some things that you have wanted to read about or study that are above and beyond what we do in the classroom or in your other extracurricular activities. Newton was at a point during this plague where he was allowed out to go socialize with some other individuals. And one of the people that he socialized with was Robert Hooke, the gentleman that gave us Hooke's Law and many of the other topics that you have studied in your other science courses. As I've mentioned to you before, Hooke probably would have been world-renowned in the world of physics if it wasn't for Newton. And Hooke and Newton had some conversations, and one of the things that the way the story has been passed down, the story goes, is Newton was asked to prove why an apple falling on Earth or an object falling on Earth. The apple is sort of a folklore, but an object falling on Earth towards the Earth was the same force that was causing the moon to stay in motion around the Earth. And Newton said, I believe I have that information, went home to his house, could not find the papers, and over the next few months developed his 3 laws, the law of universal gravitation, which we're going to be studying here, and calculus. So the law of universal gravitation says that all objects are attracted to all other objects according to the equation that you see here on the screen. F is equal to big G, which is a constant. A constant is a number that makes the equation work. There is a relationship between circumference and the diameter of a circle. The circumference is equal to the diameter times a factor that makes it work, a fudge factor, and that factor is pi. And the same thing happens here. There are about 20 constants in the universe. They're numbers that make equations work out correctly. And we'll talk about how we got this G value and what it is. But ultimately, Newton knew that there was a relationship between force and the mass of objects and the distance between the objects. And then G comes along later to balance out the equation and make it not just proportional, but mathematically precise. Gravitational force is, again, a mutual attraction between two objects. It is an attraction. It does not repel. When we talk about electrons and protons, we talk about the fact that electrons and protons are attracted to each other, but two electrons and two protons are repelled from each other. That's going to have a similar force to this gravitational force, but in terms of gravity, gravity only attracts two objects together. So it's a mutual force of attraction. I'm going to go through and solve some problems with this in a separate video. For now, I'm just going to cover some of the topics and do some derivations. So we'll actually do a problem in a later video. The gravitational constant, as you can see here, is 6.67 times 10 to the negative 11th newtons. Newton meters squared per kilogram squared. This is this equation as a whole, big G m1 m2 over r squared, is what we would refer to as an inverse square law, which means that as an object is pulled further apart from another object, it is going to have a decreasing force, not in a one-to-one relationship, but as a square relationship. So if you double the distance, you are going to quarter the force. Now, this equation and these ideas of inverse squares affect not just planets and stars, but they affect you. They affect things around you. If you are standing near someone and talking to them, they have a mass, you have a mass, you are attracted to them, they are attracted to you. And so the force of attraction is between any two masses. Right now, I'm holding my stylus in my hand, and this stylus has a very small mass, but it is just a few centimeters away from my head. And so there is a force of attraction between the stylus and my head. I am sitting in a chair at my desk with wheels on it. Although I am not moving right now, the filing cabinet behind me has mass, and that mass is pulling the chair and me towards it, and I am pulling the cabinet towards me. The reason I am not moving right now is because there is enough friction to hold both objects in place. And if there was no friction, we would still start to move towards each other, but our masses, when we start doing problems, we'll find that our masses are so small that the acceleration is very small, and it would take a very long time for the objects to come into each other. But ultimately, all mass is attracted to all other mass, all of the time. Why is this true? Well, the interesting part of this is Newton himself couldn't tell us that. It would take another 200 plus years for Albert Einstein to come along, and he is then going to be able to tell us exactly what happens here. Einstein himself is going to make what we're going to refer to later on as the general theory of relativity, which will explain that. That's a much deeper topic. We'll talk about that more in physics too, but in general, what we care about now is the mathematical relationship between objects that is creating what we refer to as gravity. The explanation of why it happens in detail, beyond that masses are attracted to each other, is something that we'll have to wait to talk about at another time. The gravitational constant, again, Newton did not know why masses were attracted to each other, but he knew that there was a relationship. The bigger the mass, the bigger the force. The further they are apart, the less the force. That's a proportionality concept. So if you double the distance, you quarter the force. And so what Newton did was just sort of leave it at an approximation. And along comes Henry Cavendish, who the Cavendish lab at Cambridge University is now named after. And he does an experiment. He does a number of experiments. He was an experimental physicist, but what we would today call an experimental physicist. But he does a number of experiments. And as you can see here, this was done 71 years after Newton died. And so Dish does is he takes heavy, dense spheres of mass, and he hangs them, as you can see in this picture here, and this is called a torsion balance. And so what he does is he lets the this beam that is located right here swing on a single string, and he measures the acceleration of this by looking at the change in position over time. And so he measures it using kinematics, what we call kinematics, and he is able to work his way backwards and calculate the exact forces experienced by these balls. And once he has that acceleration and he knows their mass, he can use that to find the force. In terms of gravitational constants, today we find them using more precise methods. We can use lasers that helps amplify the acceleration. If you've ever taken your watch or a piece of mirror and you had light shining on it and you just move it a small amount, you can make the arc across the room move a greater distance, because a small angular displacement can create a big linear displacement if the radius is big enough. And so what we're seeing here is that by using a laser and a mirror, we can make more precise measurements than just standing next to these spheres with a ruler and measuring them every couple hours, and only getting a small millimeter change at any given point. We also have a device like this, which again uses the same concept, but this is more of a tabletop version of it. And this is something that we could buy today and experiment with. It's very precise, it's very expensive, but it does do the trick to help explain this process. We will talk about some of the applications to universal gravitation more in our next video.